I always think of the fan on, and then I pile on.
I like doing that too, but it's just like I do it now. It's like
No, you're first.
yeah, I do it with someone else. Like, oh, it gets so hot. I swear, I like it.
Then you could really realize.
I'd be so,
You get like a yard
I would be so bored.
Yeah. I did. I used that last week. Oh,
So to the next chat meeting, everyone's like.
it's
I know, I know why.
They're so overpriced.
Yes.
Just had them.
What?
Oh, man.
what's the issue?
Well, the first thing was my camera wouldn't come on for the meet. And then this wouldn't come on. But I think we're fixed. All right, guys. So I might make a little pivot today. And so we might not get to what I really wanted to talk about. But I wanted to talk about something that shows up on our state tournament a lot, which we will have this year.
Scary.
Albeit it's a little bit later than it normally is.
What do we know what week it is?
Yes, it's April 9th through 11th. That doesn't mean we're going to take a 3-day test.
I think that's.
It means we'll pick one of those days and test on that day. But we have to test at one particular time. So,
I think
does everybody have one?
it's about like Friday, Saturday, Sunday.
Yes. And I really don't see us doing it on a Sunday.
Yeah.
So my thought is probably on a Saturday morning, because I figure if there is a conflict, it probably, and if y'all have, anybody play soccer in here? Anybody play, I know we have some baseball players too. Yeah, so if you guys have a schedule and you want to show it to me, we can kind of figure something out. I mean, it's possible, although I don't really want to ask, to try to do it during school. I know ideally that would be great for you, but it's a nightmare for everybody else that would try to coordinate that. Just trying to find a place for 110 people to test would be something. It would not be an overly big deal though to like on a Saturday morning to just yank a bunch of desks out in the pod, spread them out 6 feet apart and test you guys that way. So that would probably be easier, doing it like on a Saturday morning at 8:30 to 11. And that would give us time to kind of get you all situated and whatever. So that's probably what we'll do is that Saturday the 10th. So if you have conflicts, is show choir even up and running this year? Don't really know? But you don't have a schedule or anything like that?
There's kind of a competition up in the air sometime in April. I don't know.
Okay. Well, if you could try to find that out.
I'll let you know.
Okay, that'd be great. And same thing with soccer. If you guys have a conflict, they're only doing it that weekend. On the 10th?
Yeah, we're good.
You're good. And baseball, if you could look too, I know I got a lot of baseball players. If we have something, if we're free on the 10th, yes.
This isn't a select week. I have a club volleyball tournament on April 10th.
Okay, but at what time?
It's all that.
Here in town?
It's in Birmingham, yes.
Okay, well, there might still be a chance. We'll figure something out. There's bound to be a conflict with something. So I get that. So we'll figure it out. But anyway, we'll look into that track too. Yvonne, I know you do track. If anybody else tracking here? Well, I know you're tracking here. Okay, so if you guys have something on the 10th, yeah, Anderson, if you guys, I don't know what everybody does, but if you guys have something on the 10th, I know you because I just saw you running across my Instagram page. Good job.
Thank you.
Anyway, but if you have a conflict on the 10th for the Homewood track, if you have a conflict, let me know because that's probably when we'll do it. Okay. Anyway, what I want to do today is, it used to be in the olden days, they would just give a little polar graph up there and they would say, what's the equation of this polar graph? Or they would say, how many petals are, and they would just give you the equation. Or maybe they give you the picture of the polar graph and they ask you what it is. And they would always ask about a cardioid, or a lemniscate of some sort, or a rose curve. But later or lately, they've been throwing curveballs at us. And the curveballs are on this page. Now, I have kind of this in your book already. So if you go to your book on page like 55, you'll see a front and back variations. I think it's 55, is that right? Yeah, and it's crap. So you can take that sheet, I think it's just one page. Yeah, you can take that 55, 56 out. There's actually a typo in it anyway. It basically is memorizing. And I was looking through it yesterday and I'm like, man, my brain hurts with all the little things I had to memorize. So what I want to do, and last year was the first year I taught this, extra stuff. So what I want to do this year is kind of walk you through a better way of looking at these. And it probably will help you with the rose curves too. Okay. Now you are still going to have to memorize a couple of patterns because there's four kind of situations here that I have on the front back of what I just handed you. But I think what I'm going to show you today is if at the very minimum, if you can categorize what's happening, it'll be easier for you to actually sketch these. And then what you learned today, I think is going to help you also with the rose curves. Now, if you remember yesterday, we were talking about rose curves and we said cosine always happened to have a pedal at 0 degrees, right? Now, if you really think about those cosine, those problems, they were stuff like this, right? You had maybe a 7 cosine of a 3 theta. And the reason why is you had a pedal at 0 was because if you really think about it, the very tip of the pedal represents the furthest distance away from the pole, right? Now that occurs in maybe a bunch of spots. In this one, it occurs in 3 places. But because we know how they're spaced, if I can just find one, and there's 3 pedals, I could divide 3 into 360 and get 120. As long as I can find one, I can space the other ones 120 degrees apart, right? So the task was to find one. And right here we said, oh, it's kind of nice because cosine's always at 0. Well, that's not true if I negate this. Now, the thing is, I don't typically negate it, so you don't have to worry about that. But what I'm kind of doing, and I think I'm hurting you a little bit, is I am actually making you memorize stuff. So I want to kind of, again, pivot around and talk about why the pedal is why a pedal is located somewhere, but it's because the R is maximized there. So if you think about maximization right here, which is kind of a calculus topic, if you think about where something's maximized, the biggest R value can be, if you start thinking about the cosine, the biggest it can be is 7, because cosine ranges from what to what? From 1 to -1, if you think about the cosine curve, right? So if I want to know where cosine is going to be maximized, in this case, I mean where R is going to be maximized, in this case, R would be maximized when this is 1. Are you with me? And if that is 1, then 1 times 7 is 7. And if I can find that angle, I know where to mark the cosine. Now, if there was a negative out here, where is R going to be maximized? When all of this is what? -1. Because -1 times -7 would be +7. So I want you to be able to look at these graphs and say, when would the biggest R value possibly occur? And then once you decide that, like in this case, once you decide that, you can take this. Let me go back to the positive one. You can take this, set it equal to 1, and solve. Now, the solving part we've already learned, and you're going to see it's going to be a little bit more of the same because it always seems like you're setting it equal to 1 or -1 over and over and over again. But if you think about it, what angle gives cosine a value of 1? Think about the unit circle. On the unit circle, what angle is cosine 1? Where? 0? So if it's 0, that means your 3 theta is 0 degrees, and therefore when you divide by 3, theta is 0. Now that's why all of my cosine rose curves were pointed at 0, because it really didn't matter whether it was a 3 or an 8 or a 10. When you divided it, you always got 0, right? But I'm kind of making you memorize that way, because now if you think about it this way, you're going to have a better plan. Now when is R maximized? Now R is maximized when the cosine value is -1. Where is cosine -1? At 180? So now you have a pedal where? At 60. Now you have a plan for finding a pedal no matter what. So you go and you mark your first pedal at 60 degrees. There's still 3 pedals, so they're still 120 apart. So once you mark that 60, then you go 120 to get over to 180, then you go another 20 to get 300, and you've got your 3 pedals. And now you have a plan that works for all of these, including everything I do today, even when they start getting really whacked up. Are you kind of seeing this? Now think about what we did with sine. If I have a sine graph here, we talked about how sine, they don't have a common pedal. But now you don't have to think about sine any differently. If you look at this, you can say, all right, where is R maximized? R would be maximized when sine is what? 1? So, no, when sine of 3 theta is 1. When is sine of 3 theta equal to 1? When the angle is 90, and the angle is 3 theta. So when 3 theta is 90, I divide by theta, and I find my first pedal is at 30 degrees. And you mark your 30, and again, if there's 3 pedals, they're all 120 degrees apart. You go to 150, you go to 270, and you have your 3 pedals, and you sketch it out. And if I happen to sneak a negative in there, you don't freak out anymore because you go, oh, R would be its biggest if that was a -1, because -1 times -7 is 7, right? So if that was a -1, where is sine of -1? Right, not at 90, but I'm going to go with -90 because it's just easier than 270, but you could use 270. So if I say -90, where's your first pedal? -30. Are you seeing this? Now you could use 270 and you would get one at 90 degrees, but that's okay, right? Because right here, there's -30. If I did it this route, if I chose to use 270, I'm going to get a 90, which is up here. But again, you're going to get all 3 of these pedals because they're all 120 degrees apart. So whether you use a positive or negative angle, you'll still be fine. Are y'all seeing this? Now, if you get this, not only are you going to be great shape for sine and cosine, you don't have to memorize so much. You don't have to memorize like, oh, wait, what cosine? Oh, yeah, that's always at 0. Oh, sine. Oh, I got to pull out my 3 theta equals 90. You don't have to memorize anymore. You can just think that way. And then it's going to help you with these. Now, with the graphs you've seen up here, you're going to have to learn something. Okay, the something you're going to have to learn is all of these are kind of a combination between a limacon and a rose curve. Now, you remember the limacons had the a+b thing going on, right? But they all had a 1 right there, right? But now you've got the n right there. So it's kind of like you've got this rose curve looking thing with also this limacon thing out front. And they end up having lots of different kinds of shapes. And I categorize this down into 3, maybe 4 situations. The first one is, you can look at all of these. These are all the cosine ones, all right? So these are all a bunch of cosine examples. Actually, there's some sine examples. Oh, that's supposed to be sine right here. Change that. I knew I'd have some typos because I changed that to a sine. This is a cosine. So if you ever have something with the sine or the cosine, but the A is smaller, and you can see right here, the A is smaller than the B. You see that? Yes, no? If you see that, you're going to have these big pedal, small pedal graphs. The sine curves have the small pedal in between the big pedals. Are you seeing that? The cosine curves have the small pedal in the interior. But if you look at all of these, what do you see about the 4 or the 5? If you had to talk about what the 4 was doing or what the 5 was doing, what could you say? Number of big pedals. So the number right there represents the number of big pedals. And aren't the big pedals the furthest distance away? Right? So that's where it's maximized. So if I asked you, if you were looking for where a big pedal existed, I would want the biggest R value, just like I did on a rose curve. So when you look up here, what value of this would maximize R? When sine of 4 theta equals what? Equals 1. Now don't worry about the angle. When the sine of the 4 theta equaled 1, right? Because when all of that's equal to 1, you get 2 plus 6, which is 8. So you want to find out, where is sine of 4 theta equal to 1? Well, it's when 4 theta is what, Ella? 90, right. So when 4 theta is 90, or when theta is 22.5 degrees, and there it is. So if you already know, which you're going to have to learn in this part, if you know that when the small number's up front, you got big pedal, small pedal, if you know that, then you go, well, let me find the big pedals. You mark that first one. There's 4 big pedals. So you go every 90 degrees and mark those. And then you go, all right, well, sine has the little pedals in between them. So then you go over a 45, since the total was 90. And you go 45 there, and then you do 90 between each of those. Are y'all seeing that? Or I guess from right here, you could just go 45, 45, 45, 45, 45, 45, 45, and then just go big, small, big, small, big, small. And if you're wondering, how do I know how long the big one is? The big is out there to 8. How do you think you found that? 2 plus or 6 plus 2. The small ones have a length of 4. How do you think I found that? 6 minus 2. Are you seeing that? Now, that's true. Let's go to this one. It's a slightly little bit different. Right here you have R equals 2 minus 6 sine of 4 theta. How am I going to maximize R there? What would the sine of 4 theta have to be to maximize the R? A negative 1. Because if that was a negative 1, that changes the negative 6 to positive 6, doesn't it? And then you'd have a biggest R value. Well, when is sine of 4 theta negative 1? Not at 90. Where? At 270 or negative 90? I like the negative. So I divide and I get theta equals negative 22.5. And that is right there. So if I know where the first big pedal is, right, and I know there's 4 big pedals and 4 small pedals for a total of 8, at that point I can go, well, I could either do one of 2 things. I could go 8 into 360, right, which goes 45 times, and go 45, 45, 45, 45, 45, 45, 45, 45, and then just go big, small, big, small, big, small, big, small. And again, big pedal, 2 plus 6, because you're maximizing. Smallest pedal, it's going to end up being 6 minus 2, or 2 minus 6, whatever that 4 is going to be where it's minimized. Y'all tracking with me? Now, the exact same thing happens here with the cosines, with one small exception. Here, I'm thinking, where is R maximized? R is maximized when cosine of 5 theta is what? Is equal to 1. Where is cosine of 5 theta equal to 1? When the angle 5 theta is 0. So when theta is 0. So I go to 0 and I mark my first big pedal. And you just have to remember on these, again, there's 5 big ones, but the 5 small ones are in the interior. They're almost like inner loops. All right, so you're going to have to learn there is a, if you have an A smaller than B, big pedal, small pedal, sine, little pedal is going to be in between the big ones. Cosine, little pedal is in the interior of the big ones.
So is positive cosine always going to be on 0 and negative cosine?
I am not going to memorize anything, and the reason why I'm not going to memorize it, because I could, if I was a math team tournament guy, I could always throw curveballs at you. So I'm always going to be thinking, how can I maximize this R value? What's the biggest it can possibly be? And if I think about the numbers of what this would make that the biggest, then I'll be able to find my pedals. Although I've never seen where they throw the negative out in front of that. If it were me, and they did throw a negative out in front, rather than coming up with a whole bunch of rules, what you could do is go, you know what? Like, for instance, if that was a negative, I could factor a negative out and then say, all right, where is this maximized? Just think with me for a second. Where would that be the biggest possible value? If cosine of 5 theta was what? Negative 1. Where's cosine negative 1? 180. And then divide 5 in there. 36. But wait, there's still a negative. So if I maximize on this problem, I would say, all right, if I maximized at like 36 degrees, which would be 8 right there, this is saying it's really negative 8 at 36 degrees because there's a negative out front. So how would I do negative 8 at 36 degrees? Go back the other way. So I would go back here 8. But again, once I have my pedal, I'm home free, right? Because once you have one pedal, you know that there are 5 total pedals that are big. You divide 5 into 360, you get 72 degrees. And every 72 degrees, you mark a big pedal. And because it's cosine, you put the little pedal on the interior. So it's all, to me, about recognizing what kind of graph it is, and then finding one pedal and letting that be your guide for everything else. But again, this little thing about the negative, that's something that I've never tested anybody on. But you never know. And remember also, you could always plot points, couldn't you? Like if I gave you a bunch of these graphs with one and said match, couldn't you just say, all right, let me just plug a 0 in and see what happens? If I plug a 0 in and I got 0, this certainly would not be my answer because R is not 0 here, right? If I plugged pick another angle that you're kind of comfortable with or whatever. If I plugged in 22.5 degrees, I should be getting 8. Well, if I don't get 8, well, it's not this one. Maybe it's one of these smaller ones. So you could always guess and check and whatever, but when it comes to sketching them, you're probably going to have a better plan than just plotting points, or you're going to be plotting a lot of points. So this is the first kind if you have A smaller than B with sine or cosine. Now, here's the second kind. A bigger than B. All right? Now, if I have, this is the same sheet you have, right? I'm not looking at last year. Yeah. So what happens when A is bigger than B? Now, when A is bigger than B, let me ask you a question. Is it even possible to have an R value of 0? This is going to help you on this. I can't get an R value of 0. I'm starting with 6. The biggest sign, or the smallest sign could be is a -1, right? So the most I could possibly do, the most I could possibly reduce R by is a -2 right here. So the biggest R could be would be 6 plus 2. The smallest it can be 6 minus 2, right? So that if you ever see these where the A is bigger than B, you're not even going to get a rose curve looking thing. You're never even going to hit the pole. You're going to have this starfish looking deal that just kind of whatever has some extensions on it, and it kind of comes back a little bit, but it really doesn't ever hit the pole and create these little mini loops. All right, and if you really think about those mini loops, the mini loops even on a Lemniscate were created when the A was smaller than the B. It kind of gave you a negative value. That's what gave you that interior. But when it's bigger right here, when that's bigger than that, that's almost like a convex Lemniscate that never hit the pole. And you can kind of see that here. So again, but you want to find the biggest pedal, one of the extensions. Well, how would you do that? What would maximize your R value? When sine of 4 theta is what? Is +1. So you set sine of 4 theta equal to +1. Where is what would 4 theta be to maximize sine? 90, 4 theta equals 90, you divide, you get 22.5. All right, jumping over to here. I know we said, oh, cosine always has a value at 0. No, it doesn't. I mean, it has a value, but it's not maximized there. But you don't have to memorize that anymore. Because if I give you this and you go, oh yeah, 6 is bigger than 2. Whenever 6 is bigger than 2, that gives me one of those extension weird starfish looking things. If you have that part down, I'm like, okay, great, I got that part down. Let me find out where one of those legs is, one of those furthest parts out, those extensions. How do you do it? Well, how would I maximize this? What would this have to be? -1. So you set that equal to -1. Where would cosine be a -1? When that is 180. And where is that 180? At 36 degrees. So, and how big would it be? It'd be 8 at 36. So you go, all right, at 8, I'm going to go 15, 30. That's 45. So let's just call that 36. And then if there's 5 pedals, right? There's actually 5 big extensions. So if there's 5 big extensions, what do? 5 into 360 goes 72 times. Add a 72, add a 72, add a 72, add a 72. And those where all the big parts are. And then no, there's no small parts, but it does dip in. So if it dips out, it goes out 8. What do you think it dips in? 4. So you go in between those, right in the middle, go 4. So you're going to be going out 8 every 72. And then in between those, you're going to be going 4. And those are also 72 apart. How are we doing? Okay, so A bigger than B. Now, what about, and all of what I'm saying right here is the same thing, it's just I'm making it where if you're absent and you were just reading this, it would make some sense. Now, A equal B. Now, think about it. What do you think happens when A equals B? You don't have a loop, right? Because you can't possibly get a negative. If you look back at the very first page and the second page, here's the second page. I can't get a negative R value out of this. It is impossible, right? Think about it. There's no way if I start with 6, even if I subtract the biggest thing I can here, which would be a -2, I can't get a negative. The loops are made by negative R values. So there's clearly no loops here. Look at the first page. Lots of loops. Why? Because there's lots of possibilities for negative R values, right? R can be negative when that's a -1, right? 2 minus a 6. Negative R values give you loops. Are y'all seeing that? Yes? So if just like they did with limacons with inner loops. So negative R values occur, those are the lengths of my loops. But look at back to the third example. This would be your second page on the front. When they're equal, there's no way to get loops. No way. So what's the length of each loop? 0. So you could argue, oh yeah, there are 6 big petals and 6 small loops with a length of 0. So you could still kind of think the same way you did with the first set of graphs, except your loops don't have any length. Are you with me on that? Now, if I gave you a picture of this, my guess is you're looking at it going, why are you trying to give us some other way to do a rose curve? Right? I mean, it looks like a rose curve. All right, well, let's think about it. How would I make a rose curve there? Rose curves, they go out 8, so 8. There's nothing right there, so it's probably a sine graph. And there are 6 petals, so wait a minute. If I put 6 there, how many petals are there supposed to be? 12 on a rose curve. If I put 3 there to double it, wait, how many petals would there be? 3. So how can I possibly even make that? Well, I can't with a rose curve, right? Even though it really looks like a rose curve. So what we have to do to tweak these is create a sine graph like these. Think of it again as big petal, small petal, but the length of the small petal is 0. So all that shows up are the 6 big petals. Are y'all seeing that? But same thing, if you recognize that from this, if you see that picture and you go, all right, well, I need to find out where one of those big petals is located. Again, when would you maximize R? When this is what? Okay, we'll do this one. When would you maximize R? When this is what? A -1. Where is sine of 6 theta equal to -1? When 6 theta is what? 270 or -90, whatever. I'll use 270 this time. And if you divide by 6 into there, you get 45 degrees, right? So you have your first big petal at 45. If you chose -90, you would have gotten -15. And if you know that there are 6 big petals, how many degrees apart should they all be? 60? So 60, 60, 60, 60, 60. You're good. And your small petals would be in the middle, but there aren't any small petals because there's no way to make an R negative. Now over here you could go, wait though, that I can do with the rose curve. You're right. And I would take either equation. Like if you looked at this right now and said, wait, why can't I use 8 sine of 5 theta? 5 theta would give me 5 petals. You're absolutely right. I've actually graphed this and I've graphed this, and the only difference is your petals get a little fatter. But you're not going to notice that, nor am I. So if you wrote this for this one, great. If you write this for this one, awesome. I do not care if I gave you a problem like that. Are y'all seeing this? So anytime you have the sine ones that are odd, very true that you could actually get two different versions of this. And by the way, this would go with that, but you're kind of getting into a little sketchy territory. How do you make it a negative 18 right there? You'd have to do this, a negative out there. Because instead of graphing the 18, this would put the 18 right here. If you put a negative, it flips that 18 over to this side, and that's where you see it. It flips this down here, and that's where you see it. It flips this over here, and that's where you see it. But again, if you look at these, you can really graph all of your rose curve looking things with these models right here. But you kind of are forced to do it in these because I can't get an even number of petals, guys. I mean, I can't get certain even numbers of petals, like 6. Where would that come from? I could get 8, because 8 would be 4 with the rose curve double. You got tracking with me? I know I'm throwing a lot at you, but, and then here's the final one. What's the difference between that and this? Those are all sines. These are cosines, but do you really see a lot of difference? I don't. Again, I would look at something like this and go, all right, I've got the 4, 4. This is kind of a cross between and I don't know why I have this what. Actually, I do because that was old. I just forgot to give them the word. But right here, where would, for instance, where would this be maximized? R, when this is a -1, and where would, what angle would give me a -1? 180, right? So theta would be 30. There's 30 degrees. Mark it. How far would it be out? 8. How many big petals? 6. How many small petals? 6, but they all have a length of 0, so I don't have to mark them. So I just mark all the 6 petals 60 degrees apart, and I'm good. So when the A is smaller than B, what do you end up having? Run through it again. When A is smaller than B, you get the big little loops, right? When A is smaller than B. And remember, on all of these, on every single one, we're not doubling the number of loops, really. We're not thinking that way like we do on rose curves. On rose curves, we're thinking double the evens, keep the odds. But on all of these, we're thinking number of big petals. So when A is smaller than B, on all of those, when A is smaller than B, you're going to go, all right, there's 4 big petals on all of them, or 5 big petals on all of them. But if it's sine, your baby loops are where? In between them. And if it's cosine, your baby loops are in the interior. And the length of the big loops is A plus B. The length of the small, or B plus A. The length of the small loop is the difference there. And if you want to think about it as a negative, fine, because you're going an opposite direction for that loop. And if there are 4 big ones, the big ones are 90 degrees apart, right? And then the little ones are in the middle, so they would be 45 right here, and then those would be 90 degrees apart. And that's true whether they're on the interior or they're on the exterior. They're still, each of the littles and each of the bigs, in this case, would be 90 apart. In this case, would be 72 apart. Right? And then remember, when A is equal to B, when A is bigger than B, you don't have the little loops. You can't hit 0. It's impossible. That's when you have the starfish looking things. And remember, you're not just marking how far out it goes. You're not just marking that. You're also marking what? How in it comes. So it's kind of like marking big loops and small loops, except they're not small, are they? They're just kind of connect the dots, which makes it a little easier to graph, I think. And there's really, other than, in this case, there's really no difference between sine and cosine. You're just marking the bigs and the smalls and then connecting the dots into a little starfish looking thing. You don't have to actually think about loops being on the interior or in between them or on the interior, like you did before with sine and cosine. And then again, back to where it's equal. If it's equal, your baby loops shrink up, whether it's sine or whether it's cosine. And as long as are gone because a minus b is 0. What do you think?
Good.
All right. So on your test, which is usually what I think when I get smacked in the face with some material, I'm not going to count these as much as I count the other ones. Like on the other ones, if I say, hey, graph this, and I give you a blank polar graph like this, that would be like problem 4. If I give you these, I would give you, if I gave you, say, this one and that one, this would be 4A and 4B. So if everything was a 4-point problem, these would be like 2-point problems. In the past, people have done well on them if you bother to actually learn and see those differences, but it shouldn't be overwhelming. I don't think, should I throw those out? And I give you a little bit of practice once you go through all 3 of the reviews. But make sure you go back and refresh yourself. I think these notes that you currently have are much better than the ones I had last year, which were all about memorizing. And I really do think at the end of the day, this is going to help you with rose curves too, because it forces your brain into thinking about where's that first pedal, as opposed to just memorizing things like, oh, if it's a cosine rose curve, there's always one at 0, which really isn't even true, because I could change that lead number to a negative. Are you with me? All right. Sweet. All right, well, here's what we're going to do at this point. Do whatever it says on the homework tonight, which I think it's going to say work on review number 2. Well, I'm not done. Yeah, it says start looking at review number 2. I want to start, wait, in the 8 minutes I have left, I want to start talking about projectile motion. Okay, so we're a little bit behind. I'm not worried about that. If we don't catch up, I'll just bump everything back a day. So I'm not worried about it a bit. Don't stress.
What about the R squared?
Oh yeah, no, Lemniscates. Totally forgot about those. Looks like I will not start on projectile motion. So jump back up to before these notes. There's a couple problems that we did not talk about. They're called Lemniscates. They're the only ones that have R squared in them. Okay? So if you see an R squared, you'll know it's a Lemniscate. And you'll also know if there's an R squared, that kind of doesn't fit the model that I've been doing, right? Everything I've done is R equals. So think about this for a second. What if I were to go back and write it as R equals by square rooting both sides? What would happen if I square rooted this? I'd get what? Plus or minus 4, because I could, if I square rooted both sides, but the cosine 2 theta would still be stuck under here, right? Let me ask you a question. Are there certain values of theta that when I plug them in here, double them, and then take the cosine of it, they're going to spit out some positive numbers, right? Like, for instance, if I plug 20 degrees in there, cosine of 40 is a positive number. But what if I put something like 60 degrees in there for theta? Then I go 60 times 2 is 120. What's cosine of 120? That's negative a half. What happens when I square root negative a half? I get an imaginary number. Is that going to show up when I graph it? So there are actually some pedals here that don't show up, which kind of makes sense. Because if I square root both sides, if I just look at this and square root both sides, to me, this really does, and I don't simplify, this looks a lot like a rose curve to me. I mean, doesn't it to you? I mean, rose curves had a 2 with a theta and a number out front. The square root is obviously changing that R value, the maximum R value, to what? It's not 16, is it? 4. So the length of R, the length of the pedal would be 4. And the 2 right there makes me think that because it's kind of a rose curve, that I would have 4 pedals, right? All right? Problem is, you just told me certain angles are going to make certain pedals have imaginary answers. Well, that's going to get rid of half your pedals, because half of the time cosine's negative, half the time it's positive. Well, the upside of this is, that's a lot to throw at you, but the upside of this is every lemniscate that we're going to do, every one is going to have 2 pedals. And all you got to do is find one of them, because the other 2, because we're only going to do lemniscates with a 2 there, okay? Not with a 3 or 4 or 5 or whatever. So if you see a 2 there, you're going to go, oh, and an R squared, you're going to go lemniscate. The pedal's biggest value is R is going to be 4 because you're square rooting both sides. And then you got to go, well, where would there be a maximum pedal? Well, where would I maximize the R value here? When cosine of 2 theta is what? Is 1. Where is cosine of 2 theta 1? When the 2 theta is 0. When is the 2 theta 0? At 0. So you just come over there and you mark your first pedal at 0. One pedal at 0, another pedal 180 degrees apart. Because at 90 and at 270, when I plug that in there, I get nothing. And there are other values right there that give me imaginaries. And you can try it, but those are the only 2 places where R would be maximized. So just find the first pedal and then mark another one, and you've got a little propeller looking thing. And if it happens to be a sine curve, same thing. If I was square rooting both sides, I would get R equals 4, and then the square root of this. Well, the biggest R could be is 4. Where would that happen? When sine of 2 theta is 1. When would sine of 2 theta be 1? When 2 theta is 90, right? Or when theta is 45. And just like we've been doing, I'm going to go out to 45 degrees. And I would love to mark all 4 pedals, but 2 of them are going to work, 2 of them are not going to work. So I just mark that and the one opposite it, 180 degrees, and I mark the 2 pedals. Y'all with me? So that's all you have to know on Lemniscates. And yes, I can make all these, I can throw tangents, I can make 2, 4. Those are all different graphs, but they're not graphs that we're studying in polar and pre-cal. Y'all with me? I'll tell you what I want you to, well, no. Just work on review number 2. Make sure when you finish that review number 2 that you either come in here tomorrow really feeling confident about every kind of polar graph or come in here with some good questions. And let me help kind of straighten out your thinking. And then we're going to start projectile tomorrow. And there's an outside chance we may move this test day. And we'll just figure it out as we go. All right? All right.
Good stuff.
Oh.